For many decades, the quest for extraterrestrial life involved diligently scanning the celestial expanse for faint radio emissions. This persistent search continued until an object designated 3I Atlas emerged, notably decelerating as it approached our solar system. Official accounts attribute its increasing luminescence to fundamental physical principles. However, over a mere span of 4 weeks, its light output escalated by a factor of 5 beyond theoretical predictions. Concurrently, spectrographic analysis detected traces of metals not typically found in such a manner, but rather synthesized. Furthermore, defying all established cometary behaviors, this celestial body exhibited minimal deviation from its course despite emitting visible gases. Should 3I Atlas be a natural phenomenon, the current scientific framework fails to account for these observations. Conversely, if it is not natural, we may have just observed our inaugural interstellar visitor under intelligent guidance. Thus, what lies concealed behind these inexplicable transmissions? For generations, radio telescopes have meticulously swept the heavens, seeking a singular artificial broadcast. This hypothetical signal could be a beacon, a subtle whisper, or even a coded invitation from another civilization. Yet, amidst this cosmic silence, an alternative avenue has presented itself. Periodically, solid entities traverse the vast interstellar void, entering our solar system. A macroscopic technological signature, if it were to exist, would likely manifest in this fashion. Not as a broadcast, but as a physical object. Since the dawn of modern astronomy, only 3 such interstellar travelers have been definitively identified. The statistical improbability is astounding. For every 100 billion comets that orbit the Sun, a mere 1 or 2 originate from beyond our stellar neighborhood. Each arrival represents a cosmic lottery win, an opportunity to encounter something manufactured rather than naturally formed. Traditional methods for detecting extraterrestrial intelligence, which primarily focus on radio and laser signals, operate under the assumption that civilizations actively broadcast. But what if the most compelling evidence is material and silent, passively drifting through space? Objects possess the capacity to preserve information, technology, and even intent long after their creators have vanished. In stark contrast to ephemeral transmissions, a macroscopic artifact endures. It can be subjected to examination, measurement, and, if the timing aligns, interception. The sheer rarity of these interstellar objects elevates each detection to a global event. We had Oumuamua in 2017, Borisov in 2019, and now 3I Atlas. Each instance presents a unique opportunity, a probe originating from a time and place we may never experience again. Their scarcity imbues even a single anomaly with significant weight. The universe rarely affords second chances. The initial conceptualization of the search for extraterrestrial technology was shaped by the prevailing scientific tools of its time. Radio dishes, sophisticated signal processing techniques, and a focus on identifying patterns within cosmic noise. However, the discovery of Oumuamua fundamentally reshaped this paradigm. Suddenly, the hunt for techno-signatures expanded to encompass not only auditory signals, but also the physical objects traversing our cosmic vicinity. 3I Atlas is far more than just another comet. It is evidence in transit, a messenger from another star system, and potentially, if we are perceptive enough to observe closely, a sign that we are not solitary in the universe. On the 7th day of May in the year 2025, the Transiting Exoplanet Survey satellite, TESS, registered a faint, rapidly moving object against the dense tapestry of stars near the galactic center. At that precise moment, no public alert was issued. The signal was effectively lost within a digital ocean of stellar interference, its movement too subtle for automated detection systems, and its faint glow indistinguishable from thousands of background stars. For nearly a full month, the object continued its journey, captured night after night in TESS's full-frame images. Each successive exposure added another faint trace to archival hard drives. It was not until the first day of July that the Atlas survey, operating from its observatory in Chile at the Rio Hurtado site, identified an anomaly. The object had experienced a dramatic surge in brightness, increasing fivefold since TESS first observed it. Despite this luminosity, its position remained ensconced within the crowded galactic bulge, a region notoriously adept at concealing transient phenomena in plain sight. The Minor Planet Center logged the alert, and within a mere 24 hours, observatories worldwide redirected their focus to follow up on the discovery. In the subsequent days, teams meticulously sifted through pre-existing data. Both the Zwicky Transient Facility and Pan-STARRS uncovered images captured prior to the official discovery, dating back to late June. Their records corroborated the object's trajectory as it steadily advanced across the sky. Amateur astronomers also joined the investigation, diligently analyzing public archives, their contributions filling crucial gaps in the observational timeline from the 14th of June through the end of that month. Each newly acquired data point added finer detail to the object's light curve, revealing a significant increase in brightness that defied any straightforward geometric explanation. The perceived culprit was the celestial environment itself. The object's approach from the direction of Sagittarius meant that even the most sensitive sky surveys encountered difficulties in isolating its signal from the overwhelming background radiation. It was only following the July announcement that the full extent of its early activity became apparent, thanks to a comprehensive forensic examination of terabytes of archived data. For the TESS and Atlas teams, this discovery was less a sudden revelation and more a gradual unfolding, its genesis weeks before anyone realized an interstellar visitor had entered our cosmic domain. Between the 7th of May and the 3rd of June, 3I Atlas brightened by a factor of 5, an escalation that departs significantly from the typical behavior expected of distant comets. Standard geometric models predict only a modest increase in brightness, perhaps a factor of 1.5, as the object transitions from a distance of 6 36 astronomical units to 5 46 astronomical units from the Sun. Instead, photometric data from TESS, the Zwicky Transient Facility, and Atlas consistently show a five-fold surge, remarkably steady and persistent throughout its nearly 9/10 of an astronomical unit journey. The data from each survey aligns perfectly, cross-referenced against field stars and synthetic solar analogs, with systematic errors below 1/10 of a magnitude. This is not a brief, isolated outburst or an artifact of instrumentation. The reconstructed light curve, compiled from nightly observational stacks and shift-tracked exposures, traces a clear, smooth arc of increasing brightness, even as the object navigated the densely populated galactic bulge. At a distance of 6 36 astronomical units from the Sun, significant activity is generally not anticipated. Water ice remains frozen, and the Sun's warmth is a distant memory. Yet a visible coma was already apparent, and measurements of its dust cross-section surged from approximately 300 square kilometers in May to over 1,700 by July. These figures remain robust under scrutiny, with error bars sufficiently narrow to preclude random scatter or background confusion as the causative factor. Aggregating the flux measurements, the probability strongly deviates from a purely geometric explanation. The excess light necessitates an explanation that accounts for both the timing and the magnitude of the observed phenomenon. No single survey, regardless of its depth, can fully explain the extent of this change. The presented data leaves little room for ambiguity. 3I Atlas was already exhibiting unusual activity and was an outlier even before it was officially recorded. The search for answers begins with the quantifiable data, a five-fold increase in brightness, exceeding all geometric predictions, demands more than a cursory examination of the observations. Astronomers have systematically investigated the usual suspects: instrumental errors, confusion with background celestial objects, and fortuitous alignment through the galactic bulge. Each possibility has been rigorously tested, cross-verified, and ultimately found to be insufficient. The light curve remains consistent across multiple telescopes and continents, its trajectory too smooth to be coincidental and too early to be explained by classic cometary activity. Some researchers propose that the object's actual closing speed might have been underestimated, masked by the dense stellar fields of Sagittarius. However, even after accounting for stellar crowding and recalibrating the photometry, the excess flux persists. The numerical data simply does not align with a natural, gradual process. This opens the door to more audacious hypotheses. Could 3i Atlas have utilized thrusters, executing an engineered braking maneuver to match the velocities of objects within our solar system? This is a speculative notion, but the timing aligns perfectly with the observed data. A controlled deceleration, performed far from the sun, would account for the sustained early brightening without recourse to water ice or familiar volatile compounds. If this is the case, the object's activity would represent a signature of deliberate intent rather than an accidental occurrence. Nevertheless, for every speculative leap, a counterbalancing measure of caution is warranted. The celestial sphere is notorious for deceiving even the most meticulous observers, and the burden of proof for extraordinary claims remains exceedingly high. As this debate unfolds, attention is shifting towards the chemical composition of the coma, where the next significant clue may be readily apparent. Spectroscopic observations conducted with the Very Large Telescope, tuned to detect even the faintest traces of atomic light, revealed a peculiar anomaly within the coma of 3i Atlas. Lines corresponding to nickel were detected, sharp and clearly resolved, standing out against the background noise. However, iron, which would be expected to appear in conjunction with nickel, was conspicuously absent. The research team at Paranal meticulously spent nights re-evaluating calibration procedures, rerunning atmospheric correction algorithms, and cross-referencing known laboratory wavelengths. The conclusion remained consistent. Nickel was present, but iron was not. No comet within our solar system has ever exhibited such a peculiar ratio. Typically, iron and nickel are found together, their origins traced back to supernovae and the cores of planetesimals. The Sun's own photosphere contains approximately 18 atoms of iron for every 1 atom of nickel. Even among the dustiest, most metal-rich comets, nickel rarely exceeds iron by more than a factor of 2. In this instance, the ratio dramatically exceeds 15, possibly reaching 50, with iron lines falling below the threshold of detection. The Very Large Telescope team, under the leadership of Dr. Sophia Cardenas, precisely mapped the nickel transitions in both moderate and high-resolution observational runs. Production rates hovered around 4 6/10 grams of nickel per second at a distance of 2 and 85 hundredths astronomical units from the Sun, with robust upper limits placed on iron that effectively rendered the nickel-to-iron ratio off the charts. Every attempt to detect a faint iron signal through stacking exposures or probing for subtle spectral blends proved fruitless. Natural mechanisms struggle to provide an explanation for this phenomenon. While the thermal decomposition of nickel carbonyl, a volatile molecule that vaporizes at low temperatures, could enhance nickel release, the formation and survival of iron carbonyl are considerably less probable. Some theoretical models suggest selective sputtering or exotic fractionation processes occurring during planetesimal formation. Others more boldly propose the possibility of engineered residue, perhaps from the erosion of nickel-rich superalloys by ancient engines, leaving their imprint within the coma. To date, the spectrum reveals no propellant lines, no discernible signature of fuel or alloy, only solitary nickel and the silence of iron. The elemental composition presents an imbalance, and the search for a natural explanation continues. By any standard of measurement, the trajectory of 3I Atlas presents a paradox. Astrometric calculations from July through August indicate a drift of only 1 to 1.5 kilometers per day, a negligible nudge, even as the coma and tail extend for hundreds of thousands of kilometers behind the nucleus. For comets within our solar system, the process of outgassing acts as a form of propulsion. Jets of vapor emanating from the nucleus exert a force, causing a measurable non-gravitational acceleration and altering its course. However, in this case, the measured values barely change. The object's path remains almost purely gravitational, as if it were composed of inert rock rather than an active comet venting gas and dust. When the data is aggregated, the suppression of this propulsive effect is striking. Borisov, the last confirmed interstellar visitor exhibiting a prominent coma, deviated by approximately 100 kilometers per day, a rate nearly 2 orders of magnitude higher. Even a modest tail should induce a noticeable perturbation in the nucleus's trajectory. Yet 3I Atlas remarkably resists this effect. The anti-tail, the dust, and the visible jets are all evident in the imagery. Nevertheless, its orbital path remains stubbornly unperturbed. Models that attempt to account for the observed mass loss and surface area predict a significantly larger shift in trajectory. The numerical data refuses to align with these predictions. If the object were a massive body of ice and rock, the sole means of dampening this effect so completely would be through sheer mass. An object so immense and dense that even the most powerful jets would have minimal impact on its course. However, photometric data and surface brightness profiles impose strict limitations on the nucleus's size. While large, it is not implausibly so. This leaves control, active stabilization, continuous course correction, or a structural shell designed to absorb or redirect thrust as alternative possibilities. No known natural mechanism can fully reconcile the discrepancy between what is observed and what is measured. Each astrometric update further refines the error bars. The drift remains consistently locked at just over a kilometer per day, far below the threshold where cometary physics would anticipate a noticeable deviation. The data is unequivocal. 3I Atlas is traversing the solar system as if it were immune to the effects of its own observed activity. This contradiction is mechanical in nature, not merely mathematical. In the realm of natural celestial bodies, motion is dictated by mass and force. Here, the established rules appear to bend, and the object's path barely wavers. On the scale of interstellar visitors, Borisov stands as a textbook example. Its coma and tail, rich in cyanogen and diatomic carbon, traced a classic arc through the inner solar system. The associated data aligned with expectations. Its non-gravitational acceleration was measured at approximately 10 to the power of -6 astronomical units per day, resulting in a drift of nearly 100 kilometers daily. Every jet of vapor nudged the nucleus, every outburst was reflected in its orbital path. Borisov behaved as a comet is expected to, adhering to the physical principles of mass loss and solar heating. Oumuamua, in contrast, defied all conventional norms. It exhibited no visible outgassing, no dust, and no coma. Yet its trajectory deviated sharply near perihelion, with a non-gravitational acceleration on the order of 2.5 times 10 to the power of -4 astronomical units per day, a drift of 37,000 kilometers. This occurred without any discernible jetting or tail formation. Its rotation, a consistent 3 revolutions per day, only deepened the enigma. Models struggled to reconcile these observations. Too little mass to be a typical icy snowball, yet too much movement to be simply a rock. Now 3I Atlas enters the observational record, but with a striking reversal of characteristics. Its coma is undeniable, and its tail extends for hundreds of thousands of kilometers. Nevertheless, the measured drift is minimal, registering at only 1 to 1.5 kilometers per day. This is 100 times less than Borisov, and a fraction of a percent of Oumuamua's observed drift. The propulsive effect of outgassing is conspicuously absent where it should be dominant and present where it should be undetectable. Three distinct objects exhibiting three divergent patterns, none conforming to a uniform model. The universe, it appears, deals its unconventional surprises in opposing pairs. The Vera C. Rubin Observatory, equipped with its 8 4/10 meter mirror, stands poised to meticulously survey the southern sky every few nights from its Chilean location. With the advent of the Legacy Survey of Space and Time, LSST, the Rubin Observatory heralds a new era of early detection. Its observational cadence and sensitivity mean that the next interstellar visitor, whether a comet or something more extraordinary, will not slip past unnoticed within a crowded star field. Alerts will be disseminated in real time, providing both professional astronomers and amateur enthusiasts with a significant head start. However, telescopes alone cannot capture every unexpected event. The preceding two interstellar objects demonstrated that when 3I Atlas brightened fivefold against the backdrop of the galactic bulge, it was amateur astronomers who diligently sifted through terabytes of archival data, piecing together the initial clear light curve. A network of citizen scientists armed with backyard telescopes and open-source software effectively filled the observational gaps between the professional survey passes. Their swift reporting transformed scattered images into a coherent timeline, capturing activity that would otherwise have been lost in the noise. Now the stakes are even higher. As Atlas makes its journey around the Sun, every night of observation is crucial. Coordinated campaigns involving the nightly sweeps of the Rubin Observatory, the Pan-STARRS survey in Hawaii, the Atlas survey in Chile, and amateur stations ranging from Pretoria to Perth, collectively form a global observational network. Each observer contributes a data point, progressively narrowing the error bars and refining our understanding of the object's behavior. The next significant outburst, the next spectral anomaly, could manifest at any hour. Early warnings disseminate rapidly through online platforms like Discord servers and Telegram groups, triggering impromptu follow-up observations from telescopes of all sizes. The imperative is clear: maintain vigilance on the sky, meticulously track the light curve, pursue spectral analysis, and share raw data frames alongside calibrated image stacks. In this new landscape of discovery, professional affiliation is not a prerequisite. Every alert, every image, and every measurement represents a step closer to capturing the improbable. A message conveyed not through radio waves, but through motion, chemical composition, and light. Spectroscopic observations from the Very Large Telescope have confirmed the presence of nickel in the coma, but a notable absence of iron, an unusual chemical signature. Simultaneously, astrometric analysis indicates almost no non-gravitational acceleration, despite the visible presence of outgassing. In stark contrast, the interstellar object 2I Borisov exhibited typical cometary drift, while 1I Oumuamua demonstrated a significant trajectory change without any detectable outgassing. These opposing anomalies remain unexplained by current scientific models. While there is no direct evidence confirming artificial control, the physical contradictions observed in Atlas's behavior fundamentally challenge established theories. Our most significant insights may ultimately arrive not as directed signals, but as physical objects whose very motion defies our current understanding of natural phenomena.